Okay, so in 2.1, we looked at graphs for frequency distributions. We have other quantitative graphs we can make. So that's what we're going to look at in 2.2. The first one we're going to look at is a stem and leaf plot. And this is an example of an exploratory data analysis. Okay, we're in EDA, which is what your book uses. So each number is split into a stem which is going to represent the leftmost digits, and a leaf, which is going to be the rightmost digits. And actually, I'm going to say rightmost digit. Okay. So with this, we have some advantages. So with this, it's very easy to organize. And determine the shape of the data. Also, it's one of the few graphs that actually displays every data entry. Okay, so we have two different types. We have an unordered stem and leaf plot and an ordered stem and leaf plot. So what we want to do is we want to start off with determining what is our minimum and our maximum. Here our data represents the scores of a biology class on a midterm exam. And then we're going to describe any patterns. Okay, so looks like our minimum is 49 and our maximum is 95. Okay, so remember to always label, so we have scores on a biology test. Or a midterm, either way. And we're gonna have a stem. And we're gonna have our leaf. Okay, so remember the stem represents the leftmost digits. So we're gonna start at 4 because of the 40, and we're gonna go up to 9. Okay. And then you're just gonna fill in what you know. So 75, we're gonna put a 5 for the leaf on row 7. 8, 85, we do 8 and 5, and then continue through. Okay. And the other thing we have to make sure we include is a key. Because when you look at a stem and leaf plot, that 4-9, for as far as we know, that's 4.9. Or maybe it's 490. So whenever we do our key, we're just going to say 4, and then a vertical line 9, and then say what that equals. So that equals, in this example, 49. Okay. To make it an ordered stem and leaf plot, you're simply going to put each of your leaves in order. So again, we have our scores on the biology test. We have our stem and our leaf. Bring down our stem. Those are going to all be the same. And then our leaf, we just put in order. So we have 9, and 7, 8 for our 60s. For our 70s, we're going to have 3, 5, 5, 6. For our 80s, we're going to have 0, 0, 2, 3, 5, 5, 7, 8, and then 0, 1, 1, 1, 2, 4, 5, 5. Okay. So we can then find patterns. So there's a couple of things here we can notice. We could say that most students scored, let's say greater than. A 67%. Okay. We can also say that there's an outlier. So you can use stem and leaf plots to identify unusual data values, and these are called outliers. So here our outlier would equal that score of 49. Okay, so our next quantitative graph is a dot plot. And this is when each data entry is plotted. Wow. Using a point above a horizontal axis. Okay, so the advantages here, again, it shows the shape. Shows individual data. And again, helps identify outliers. Okay. My personal disadvantage with dot plots is they're just very tedious to make. So here, if we want to use a dot plot to organize the data to represent the scores on the biology test, again, we're going to make sure we label above. We have scores on a biology test. And we know our minimum from the previous example is 45. And we need to go up to 95. Here's the thing though, you have to make sure you include every number. So I'm gonna go ahead and just put in, go up by every 5. And then what I do is I just go back in and add 4 little tallies in between. Okay. Then you're going to go through and put a dot above each number. So we have 75, 85, 90, 80, 87, 67, 82, 88, 95, 91, 73, and then 80. So now we have a duplicate. So that gets stacked on top. Okay, so now our second row, we have 83, 92, 94, 68, 75 gets stacked on top, 91 gets stacked, 49 is on its lonesome, 95, 87 gets stacked, 76, 91 gets stacked, and 85. Okay, the other thing that's easy to find from a dot plot is where your largest frequency is. So we could say that 91 was scored most often. Which we'll talk about in 2.3, that's called our mode. Okay, so we've been looking at quantitative. Now we can look at graphing qualitative data sets. There aren't as many different types of graphs. So first one we have is a Pareto chart, and this is a vertical bar graph. In which the height of the bar represents frequency. The thing that's different about a Pareto chart is that the highest frequency is on the left, and lowest on the right. Okay, so if we look at this example, in a recent year, the retail industry lost $34.5 billion in inventory shrinkage. Inventory shrinkage is the loss of inventory through breakage, pilferage, shoplifting, and so on. The main causes of inventory shrinkage are administrative error, employee theft, shoplifting, unknown, and vendor fraud. Use a Pareto chart to organize the data. Which causes of inventory shrinkage should retailers address first? So here, our label is going to be inventory shrinkage, or our title. And let's say causes. Okay. And then again, we're going to make an XY axis. Okay, and we're going to say, let's see here, amount lost. I'm going to say in billions. And so we know we need to go up to 15.1. So I'm going to actually go up to 16. That's good. Okay. And then we're going to use our reasons on the bottom. Okay, so again, we start from the largest and go to the smallest. So here, our largest region or reason is employee theft. And then you're simply going to make a bar or a rectangle to show that 15.1. Okay, our next largest is shoplifting. To 12.3. Pretend that's in the center. And then we have 4.2. For admin error. Then 1.7 for vendor fraud. And lastly, we have unknown for 1.1. Okay. So to answer the question, which causes of inventory shrinkage should retailers address first, that would definitely be employee theft and shoplifting. Okay, so the next one we're going to look at is pie charts. These provide a convenient way to represent qualitative data graphically as percent of a whole. So here, so pie chart is divided into sectors. That represent categories. The area of each sector corresponds to the frequency. Okay, so we have the numbers of earned degrees conferred in thousands in 2007 are shown in the table. Use a pie chart to organize the data. Okay, so we're going to make a table that we have down below. We're going to bring down all of our information. So we start off with our frequency. I'm just going to bring all those down from the table. And we want to start off with finding our sample size. So our n, we're going to add up all of our frequencies. We add those all up, we get 3,553. And then we're going to find our relative frequency. So remember, relative frequency is f divided by n. So 942 divided by 3,553, I'm going to round to the nearest thousandth, is going to give us 0.265. Okay, I'm going to keep doing that. So 1,716 divided by 3,553 gives us 0.483. Then 731 divided by 3,553 is 0.206. And then 164 divided by 3,553 is 0.046. Okay, so then we want to find our angle, so that way we can make an accurate pie chart. So what we're going to do is we're going to take that f over n, that relative frequency we just found, and multiply by 360 degrees. So if we do that for our 0.265, we get 95.4 degrees. For a bachelor's degree, we get 173.88 degrees. And then we get 74.16 degrees for our master's. And then for our doctorate, we're going to get 16.56 degrees. And then I just want you to do the best you can with making sure it's accurate. So key thing, again, make sure that you are labeling. So degrees conferred. In 2007. Okay, so I'm going to start off with our largest angle, which is 173. Okay, that's going to be just short of a semicircle. Well, that's what I was afraid of. Okay. And then when you label that bachelor's degree, we include the percentage. Okay, so our percentage is the same thing as our relative frequency, but we just multiply it by 100. So 0.483 gives us 48.3%. Okay. Next would be our associate's degree, which is going to be just more than 90-degree angle. With 26.5%. Then we have our 74.16. And again, I'm just going to kind of split this apart, estimate it. So our master's degree is going to be our 20.6%. And then our doctorate or doctoral degree at 4.6%.